Okay, so we are on page 334, and we are going to talk about parallel axis theorem next. So far we learned how to find the inertia in when the objects are kind of in point mass. You use the form mr square and add up all the inertias together, and it kind of takes you to the integral at some point for a distribution of masses. And it is in this form here, I is equal to integral of r squared dm. And what you're integrating over is the mass, okay? Differential is mass here. And parallel axis theorem is if you know the moment of inertia about an axis that passes through the object's center of mass, then the value of inertia, moment of inertia on any axis but parallel to that one can be found using that new moment of inertia equals to the moment of inertia of the center of mass plus the mass times the h. H is the distance between the points from the center of mass rotation to the new rotation point, which are parallel, of course, it has to be, and that's h squared. Okay, so we're gonna see how we're gonna do this. So we are really adding this term to the center of mass moment of inertia to find the new moment of inertia. And again, this is parallel axis theorem. It only works if the axes are parallel to each other. Okay, and the distance between those two axes is h. Okay, so another way of saying like as h is the perpendicular, which means the shortest distance, right, between the two parallel axes as well. Okay, as an example, we'll find the moment of inertia for a rectangular plate rotating about its corner. So this is the new rotation point, and I would like to show you what the table 10.2 look like. So here's our table 10.2. I'm also sharing this with you guys, so you have a copy as well. Especially for the next coming up exam, I mean not this Quexam 7, 8, but the next one, the last one, 9. You will also have this one along with the equation sheet. Okay, these are going to be the only two things that you are allowed to look, but not for this Friday's exam, because chapter 10 is not included in this exam. Okay, just keep that in mind. So I'm not asking you to memorize any of those equations on table 10.2. I just want you to kind of be able to handpick which one you start with if you are applying parallel axis theorem, or maybe not, but I want you to handpick the one that you need. So in which case is our problem, example problem that we're doing in the class now? Since we have a perpendicular one, right? So it's gonna be the one right here, the last one. And the center of mass point is right at the center, just like this axis going through it. So this inertia, moment of inertia given here, is really the center of mass inertia. So it is 1/12 m a squared plus b squared, and a and b are the side lengths of the rectangle. Okay, so let's go back to the notes. And now that we know the center of mass inertia, which is this one, right? We just copied it from the table. That's how what we're gonna do. When we solve problems, we are going to look at chapter table 10.2 and handpick the one that we need. That may not be the one that we use, but we're gonna start from that table. And now, since the rotation is not from the center, okay, we're not rotating at this point, but we're rotating at this point, so that means you also need to apply parallel axis theorem. Just one more thing, if we were to draw this here, so our new rotation axis would be maybe like in this corner. Okay, so this is the new rotation axis. Instead of rotating like from the center of mass, now you're rotating here. And as you can see, those two axes are parallel to each other. It's very important. And this distance is going to be h. Okay, so this is going to be a very important thing to understand. But once you know it, it is very straightforward what to do now. So that's why this is our H here. Okay, right here. Wait. And so we are going to use this to find the moment of inertia around this pivot point given here on the corner. So the rotation is around this point now. We are going to apply parallel axis theorem. Okay, hopefully that is clear. And now let's see how we're going to do that. Couple things, like you need to understand what A and B are, and in the table 10 it's clearly shown that those are the sides. So this, we also have the same thing here, A and B, as you can see. But what is H in terms of those? So you can use this little triangle here, right? So we may need to use some extra geometry to figure things out, as we are doing here. And you can see the sides. This one is half of A and this is half of B, and you can simply find H using Pythagorean theorem. You square A half and B half, add them up, take the square root. That's going to be H. But since you have H squared, you don't really need to take the square root, so you can just keep H squared as it is, and you're just going to add these two terms here, and that gives you 1/4, because 1/2 is squared as well. So 1/4 of A squared plus B squared is what H squared is. Okay, so that's going to be plugged in to H squared. And let's do that. So the first term, center of mass inertia, is from the table, 1/12 m A squared plus B squared. And this is m times H squared. They are the same m. This is still the same mass of the rectangle, capital M. And H squared was found as 1/4 A squared plus B squared, so we plug that in here. And you're adding them up. I would make the denominators the same, so I multiply this one by 3 and top and bottom. So you get 1 plus 3 at the top, that becomes 4, and 12 at the bottom. So 4 divided by 12 is 1/3, right? And that's why you have this coefficient here. And then the new moment of inertia around this pivot point shown on the figure is given as 1/3 of the mass of the rectangle times A squared plus B squared. Okay, and this is larger than the value through the center of mass. Again, because if you look at the figure again, I'm going to get rid of my markings. So first one is the center of mass, and you look at the mass distribution and compare that with this mass distribution here when you do this. So things are much farther away from this, right? Like look at the mass distribution. That's why this case, when you rotate it around this point, you have higher value of inertia, because mass is farther away and it increases the moment of inertia. To do that, we will do that a lot. You basically, if you compare these two equations, I want you to really be able to see which one has more. So you're really comparing the coefficients. Again, 1/3 can be written as 4/12, so that's 4 times more than the center of mass, right? And that's going to be a common thing that we are going to do later on for different objects. And again, we can have many different ones, as you can see here, not just a rectangle. We will have spheres, we will have like a hoop. The first one is a hoop, and the next one is like a cylinder or a ring. You can kind of think about it as a cylinder as well, or make it a little bit like thinner, so make it a ring. Next one is a solid cylinder or a disc. So you can make that L really small and it becomes a disc, right? And this is rotated around the central axis. In part D, you can see that again, the same object, solid cylinder or disc, but about the central diameter. So rotation axis is different between part C and D, as you can see. And look at the inertia. They are different, right? Of course, it's going to be different because the mass distribution has changed. So moment of inertia depends on not just mass, but also the mass distribution. And next we have like the thin rod. I'm at part E. Thin rod about its axis through the center. perpendicular to the length, right? So you can kind of spin it, it's rotating in this object like kind of this way. And if the object was rotated from here, then you can again use the parallel axis theorem. You would say this is h would be in this case half L, and apply. So you take this is the center of mass plus h mh square, right? And then you can find the case when you rotate it around this axis. Okay, so this is how we apply parallel axis theorem. Next we have the solid sphere about any diameter. Okay, but it passes through the center. And this next one, G, is the thin spherical shell. So this is a hollow sphere, and this one is the previous one was a solid sphere. That's the difference, and you can see the difference. This is 2/5, this is 2/3. Okay, since they have the same mass, thin shell has more inertia because more mass is concentrated more in the outer edge than inside. Okay, so it changes the inertia, the moment of inertia. And this is the hoop. It's just like you can compare this H with A, same object, but axes are different. So you can see that there's a change in the inertia, and we already talked about the slab. Okay, next I'm gonna go back to the notes, and we are going to, let's see, so these are the quiz questions that you will practice, and there's a nice supplemental example here. Please try to do this. I mean, solution is already here, and in the next video I'm going to talk about second law in the rotation form.